An automobile engine is being operated with pure methyl alcohol, using 10% excess air over that necessary for theoretical combustion and securing substantially complete combustion of the fuel. A sample of the exhaust gases is removed from the exhaust pipe and carefully analyzed in an Orsat. What should be the expected volume decrease when the gas passes through pyrogalol? Did I pronounce pyrogalol right? I don't know. So, pure methyl alcohol goes inside the engine chamber. Methyl alcohol, that's CH3OH, right? Because methane is CH4. And it's burned with 10% excess air, which means there's a 10% excess plus theoretical theo air, and then it comes out as a flue gas. Now, since this is a complete combustion, all of the fuel is converted into CO2, H2O, N2. I mean, the fuel isn't converted into N2, but it's part of what comes out as one of the components of the flue gas. So, yeah. And also, the excess O2 also comes out in the flue gas. We need to find the Orsat analysis. We're not going to include water in our flue gas analysis. So let's write the required. That's an it's an Orsat. The flue gas on a dry basis. Flue gas. Or the DFG. Okay, primarily we need to find the volume decrease. Volume decrease after it goes through pyrogalol. And pyrogalol is the solvent which basically absorbs oxygen, so it takes out the oxygen from the flue gas. So we're really just trying to find out the amount of oxygen in the flue gas. We're going to set our basis as 1 mole, 1 lb-mole of methyl alcohol. So this is what you feed into the engine. Let's write the equation for the combustion. Plus O2 turns into CO2 plus H2O. Over here we have 4 H2O, 4 H's, 4 hydrogens. So let's put it 2 and H2O. So now we have 4 hydrogens over here, 2 oxygens, 4. Okay, we need 3 here because there's only 1 here, so let's make it 3 over 2. I think it's already balanced. Let's count the C's here. There's 1 C, there's 4 hydrogens, there's 3 plus 1, 4 oxygens. And over here there's 1 carbon and 4 hydrogens, and for the O's, for the oxygens you have 2 plus 2. You have 4. Okay, it's balanced. So first, we're going to calculate the theoretical oxygen. So you must remember that to get theoretical oxygen, we always have to assume complete combustion. Complete combustion. I mean, in this problem, it's already a complete combustion problem. So, you really just go into calculating with the complete combustion assumption, but if it's an incomplete combustion, to get the theoretical O2, you still need to assume complete combustion, even if not all the fuel was converted into CO2 and H2O. Okay, so to get theoretical O2, we just look at the equation. So for every 1 mole of methyl alcohol, we need 3.5 oxygen moles. Okay, so our basis is 1 lb-mole, so we need to calculate the oxygen needed for that. And it's pretty obvious. 1 lb-mole of methyl alcohol needs 3.5. So that means 3 over 2 oxygen moles. That's our theoretical O2. To get the excess O2, you need to multiply theo by 0.1, which is 10% of the theoretical. So this is just 3. Okay. Now, we need to add them together to get the actual O2. It's equal to 1.65 moles. of O2. Okay. So now we have our actual O2. We can also calculate for the N2, or the nitrogen gas that is in the dry flue gas, because all of the nitrogen just comes from the dry gas that is fed, right? It all just comes from here, from the air. So it's not going to change since it didn't react with anything. N2 that goes in is the N2 that goes out. So this is just the actual O2, 1.65. I'm not going to write moles because it's hard for me to write, times the ratio of air to oxygen, N2 to oxygen, which is 21 moles of O2 per 79 moles of N2. So 1.65 times that, we get 6.207142857 moles N2. We store this because it's a long number. Okay, so we have O2 in the DFG. Why? Because this is a complete combustion problem, and in complete combustion, the O2 in the dry flue gas is just equal to the excess O2 fed into the furnace. However, in incomplete combustion, you need to account for the free oxygen, which is the moles of H2 divided by 2 plus the moles of CO that was produced divided by 2. We'll get to that in another video. So this is just 0.15 moles. 0.15 moles O2. Okay, so let's look back. We already have O2 and 2. Now let's solve for CO2. All of the CH3OH, or methyl alcohol, was converted into CO2. Okay, so let's go back to our equation. So 1 mole of methyl alcohol gets converted into 1 mole of CO2. So we have 1 mole of methyl alcohol, right? So it all just became CO2. So we also have 1 mole, lb mole of CO2 that was produced. So we can do our Orsat analysis now. The components are CO2. Sorry, I was about to write water. O2 and N2. Okay. So our total is 7.35714, blah, blah, blah. I'm going to store that. Now we compute for the percentages. So here we have 13.59%, 0.15 divided by V times 100. We have 2.038, then 6. Alpha A divided by alpha B times 100, that's 84.3689. The required is the volume decrease after pyrogalol, after the gas passes through pyrogalol. So it's just asking us for a percentage of O2 in the gas. This is the answer. So you might be asking, but it says volume. Well, in the flue gas analysis, the volume percentage is just equal to the mole percentage, because we assume that the flue gas components behave as an ideal gas mixture, meaning Avogadro's law applies, which states that equal volumes of gases at the same temperature and pressure contain an equal number of moles. So this is why the mole fraction is equal to the volume fraction. So this is our answer. This is the volume decrease, 2.04, because that is our oxygen percentage.